Welcome. We often hear that there's too little carbon dioxide in the atmosphere to do much of anything. This video is going to investigate whether that is true or not. Carbon dioxide only makes up 400 parts per million in our atmosphere. That's 0.04%. And that doesn't sound like much. If we take 10,000 molecules of air represented by these black dots in this square here, let's put on how many of those are carbon dioxide. And it's just four. Those four little red dots in the middle, just there. Now that doesn't seem like much at all. And worse yet, it's taken over 200 years for it to get from 270 parts per million to over 400 parts per million. So where's the big problem? Is there too much carbon dioxide in the atmosphere or too little? Some say there's too little to be warming the planet and causing all these droughts and high temperatures all around the planet. While others, often the same people, are claiming that there's so much new nice carbon dioxide that it's greening the planet. As far as I'm concerned, you can't have it both ways. What we're talking about here is the greenhouse effect. That is where sunlight hits the surface of the Earth and some of that radiation is trapped by the greenhouse gases in our atmosphere. The Earth's atmosphere is made up of nitrogen, oxygen, water, argon, carbon dioxide, neon, helium and methane. They are transparent to incoming solar radiation. The sun emits most of its energy at visible wavelengths, which corresponds to the surface temperature of the sun, about 5700 degrees Kelvin. Objects emit radiation according to their temperature. So the hotter they are, the shorter the wavelength. The Earth from this energy is heated to about 290 degrees Kelvin, or about 16 degrees centigrade, and so emits infrared light at that wavelength. In other words, heat. Some of the gases in our atmosphere are transparent to infrared. We often hear that the greenhouse effect does not work. Well, let's see if it does. Just a simple experiment will prove that it does. Let's take the Earth with an atmosphere that has an average temperature of about 16 degrees centigrade. But let's compare that with another body that's the same distance from the Sun but doesn't have an atmosphere. We call it the Moon. The average temperature of the surface of the Moon is minus 16 degrees centigrade. So that shows that the Earth's atmosphere is helping our planet warm by 32 degrees centigrade. Without that effect, the Earth would be an ice planet. So how does this all work? Let's take a volume, which at the moment is full of vacuum, i.e. nothing. And if we put 100 IR photons in one end, because there's a vacuum there, 100 IR photons will come out the other end. For our first experiment, we'll fill that volume with nitrogen, and we'll call the pressure in that volume 1. It's an arbitrary unit, it doesn't matter what it actually is. We'll put 100 IR photons in one end, and because the nitrogen is completely transparent to it, we will get 100 IR photons out the other end. For our second thought experiment, we'll fill that same volume with carbon dioxide, or any other greenhouse gas. We'll fill it to the same pressure, 1, and then pass the same 100 IR photons in at one end. Now the carbon dioxide is not transparent to the infrared photons, and say there's enough carbon dioxide in there to absorb half the infrared photons that are put in the front end, so that means we'll only get 50 IR photons out the other end. For our third experiment, we're going to mix the two volumes. So we have equal amounts of carbon dioxide and nitrogen. So the total pressure in there is now 2 instead of 1. So now let's put our 100 IR photons in from the left. Now we know from the first experiment that the nitrogen molecules will make no difference whatsoever. And from the second experiment, we have the same number of carbon dioxide molecules as we had in experiment 2, so they'll absorb the same amount as before, and so therefore you'll get 50 IR photons out the far end. But note now that the percentage of the atmosphere that is carbon dioxide is only 50%, yet we're getting the same effect as though we had 100% as in experiment 2. Well, the only thing that's different is the pressure. For our next experiment, we'll double the amount of nitrogen in the volume. So once again, we'll put 100 IR photons in at one end. The nitrogen makes no difference because it's transparent, and we still have the same number of carbon dioxide molecules in there as we had in experiment 2, so they'll have the same effect, i.e. absorbing half the IR photons, so we'll still get 50 IR photons out the far end. But now the percentage of the atmosphere is 33% of carbon dioxide. So we get the same result whether we have 100% carbon dioxide, 50% carbon dioxide, or 33% carbon dioxide, because in each case we have the same number of carbon dioxide molecules in the volume. So it's not the percentage of the atmosphere that's the absorbing gas, it's the partial pressure of the gas. The pressure in each case for carbon dioxide is 1. I guess the question is, where do the IR photons go? So let's go back to experiment 2, and we'll shine our IR photons in at one end. Now some proportion of them will get through unhindered, not hitting any of the carbon dioxide molecules. However, some proportion of them won't. They'll hit the carbon dioxide molecules and be scattered in some random direction, either forwards or backwards or sideways, anywhere in the 3 dimensions. I'm sure some of you have realized that we have not yet addressed whether there are enough carbon dioxide molecules in the atmosphere to do much of anything. Let's look at some numbers to show that indeed there are. There are 2 times 10 to the 25 molecules in a cubic meter of air at the Earth's surface. The height of a uniform density atmosphere is about 1 kilometer. So if the atmosphere was all the same pressure from the surface to the top of the atmosphere, that atmosphere would be only 1 kilometer deep. So that means that there are 2 times 10 to the 28 molecules of air above every square meter of the Earth's surface. So what proportion of those are carbon dioxide? Well, it's only 0.04%. However, that turns out to be 8 trillion molecules of carbon dioxide between the surface and the top of the atmosphere. So the infrared radiation from that 1 square meter of the Earth's surface has to navigate past 8 trillion carbon dioxide molecules, many more water molecules, and some of the other trace greenhouse gases as well. So they're going to have quite a bit of difficulty getting out of the Earth's environment, and that's why the Earth is warmed. So how does an infrared photon escape from the Earth? Remember, when it hits a greenhouse gas, that photon is scattered. It can be scattered in any direction, backwards, forwards or sideways. It's much more likely to be scattered sideways or back down than forwards. How far does it get before it hits a carbon dioxide atom? That would be 70 meters. It used to be 100 meters back at the beginning of the 19th century. And it would be a much shorter distance for water vapor, about twice that for methane, and a lot longer for the other greenhouse gases. So this poor photon is bouncing around randomly in the atmosphere. This is what's called a random walk. And you can actually calculate how many steps in a random walk it would take for a IR photon to escape from the Earth's atmosphere, given the mean free path of 70 meters. So here we have the surface of the Earth, in this case it's the ocean. And what happens if it emits an infrared photon? That infrared photon may start going up, but then it could be knocked back down, sideways. Several times it might actually be back absorbed by the ocean to be re-emitted again. So this is how the planet is warmed. Eventually it will go high enough in the atmosphere that the mean free path becomes infinite and it actually escapes into deep space. That's where it cools the Earth. So let's put this whole picture together. We'll start with a mixed atmosphere with some greenhouse gases and some neutral gases, such as nitrogen. So the sun emits light at about visible wavelengths. That's where most of the energy in the sunlight is, and that's because of the surface temperature of the sun. Most of that light passes through our atmosphere without interference. The only real interference is from clouds, which we're not considering here. That light hits the surface of the Earth and warms it to about 16 degrees centigrade. As a result, the Earth re-emits that energy as infrared. Now, some of that energy is going to get out of the atmosphere unhindered, but most of it is going to start bouncing around in a random walk process. That helps warm the Earth. So let's draw some conclusions. First of all, the percentage of the atmosphere that is carbon dioxide or any other greenhouse gas is irrelevant. It's the number of carbon dioxide molecules between the surface and the outer space that makes the difference. In other words, it's partial pressure or its column density. Hence, the more CO2 in the atmosphere, the longer it will take for a photon to escape, because it has to go through more steps, and the higher it will have to go in order to find a mean free path that is long enough for it to escape into space. Both of those effects create a warmer Earth. Goodbye until next time.